So dear students, in today's class we will discuss about postulates of quantum mechanics. So if you refer any standard textbook on quantum chemistry, we will see that the postulate of quantum mechanics is described either in 5 or 6 postulates. So today we will discuss about the postulates of quantum mechanics. We will summarize the postulates of quantum mechanics in terms of 5 postulate 1, 2, 3, 4 and 5. So what is the purpose of this postulate is these postulates will guide us, okay, to understand the different aspects of quantum mechanics. So what actually quantum mechanical calculations are about, what can we actually predict about the behavior of a microscopic system or a quantum mechanical system. So answer to all this is given by these 5 basic sets of postulates, which we will call as postulate of quantum mechanics. So from the point of view of your syllabus, we are concerned only with the statements of quantum postulates of quantum mechanics. So for your examination point of view, we need to know what are the statements of the quantum mechanical postulates, but we will go a little bit deep into understanding each of this statement. Okay, without understanding the statements in some details, it would be injustice to the quantum mechanics if we do not understand what is the main idea behind setting this postulate. So let us go one by one. First, let us discuss the first postulate of quantum mechanics. Postulate 1. Okay, the statement is as follows. Okay, the state of any microscopic system. Okay, the state of any microscopic system, or you can also call it as a quantum mechanical system. Okay, quantum mechanical system is described or defined in terms of its wave function, in terms of a function, a mathematical function called wave function of the system, represented by the symbol psi, and it usually depends on x, y, z, that is the position of the particle, and it may not always depend on the time. Okay, so this is the first postulate of quantum mechanics. This is the statement, this is what you should know. Okay, the state of any microscopic system. So we are restricting ourselves to microscopic system because quantum mechanical calculations are strictly applicable for microscopic systems. Of course they are applicable to even macroscopic system, but we need not apply quantum mechanics there because classical mechanics serves the purpose. So the state of any microscopic system or a quantum mechanical system is described in terms of a function called wave function of the system. So this statement requires some explanation. So let us try to understand what this statement actually tells us. Okay, you already know what is this wave function psi. Okay, wave function psi arises because of the dual nature of the particle. A particle, in a microscopic particle especially, has both particle as well as wave nature, and the wave nature of the particle is described in terms of this function called wave function. Okay, it's represented as psi x comma y comma z comma t. This wave function represents psi of x comma y comma z comma t. It represents the amplitude of the particle wave. Okay, amplitude of the particle wave at the particular point x comma y comma z at time t. Okay, and I already told you this does not have a physical significance. Okay, the amplitude of a particle wave does not carry much physical significance, but what is important is the square of this wave function. Okay, the square of the wave function carries a very important physical information, and that is nothing but the probability of finding the particle. So though psi has no direct physical significance, the psi square, okay, if the function is a real function, or psi star into psi, this is used when the wave function is a complex function, represents or gives the probability of particle location. It represents or gives the probability of finding the particle at a particular location x comma y comma z at a particular time t. So though psi of x comma y comma z comma t has no physical significance, but it is still of very significance in quantum mechanics, because hidden inside this wave function is a lot of information about the system. So I can say that this wave function is just like a horoscope of an individual. Okay, we all of us have a horoscope with us. Okay, so if we take this horoscope to an astrologer and ask him to look into the horoscope and predict our future, okay, so by looking into the into our horoscope, the astrologer will predict our future. So same thing happens here. If we want to predict the state of the system, what would happen to the particle present inside the system in the future? Say for example, if the particle is moving in a certain direction, what would be its energy, or what would be its position, or what would be its momentum after one day, after 24 hours, or after 10 seconds. So to predict the future of a quantum mechanical system, we require this wave function. And remember, just as we are uncertain about the prediction made by the astrologer, the here also the prediction made by the wave function is also highly uncertain. It means it is probabilistic. So whatever estimation we are doing by using this wave function, it is only from a probabilistic point of view. Okay, only after doing the experiment we will come to know what is the exact energy or what is the exact momentum. Without doing the experiment, we are only able to find out the probability value of a certain physical quantity. Okay, so this wave function, as I already told you, may be a real function or a complex function. And how do you obtain this wave function? This wave function is obtained by solving the Schrodinger wave equation. It is obtained by solving Schrodinger wave equation. The Schrodinger wave equation may be a time independent Schrodinger wave equation or a time dependent Schrodinger wave equation, depending on the nature of the system. Okay, if a system is such that the different properties or physical quantities associated with the system, such as energy, dipole moment of the molecule, kinetic energy, if they are not dependent on time, in such case time independent Schrodinger wave equation can be used. If the system and the different properties of the system are dependent on the time, in such case time dependent Schrodinger wave equation has to be used. So depending on whether we are using the time dependent or time independent Schrodinger wave equation, the resulting wave function may depend on time, or it may not depend on time. So we may either end up with a wave function psi of x comma y comma z if it is a time independent Schrodinger wave equation, or we may end up with a wave function psi x comma y comma z comma t if the Schrodinger wave equation is a time dependent Schrodinger wave equation. And remember, I ascertain again, this may be a real or a complex function, but psi square or psi star into psi is always a real number. Okay, so and moreover, here we are assuming that there is only one particle present in this system. Suppose if the system contains more than one particle, suppose there are two particles. Okay, suppose there are two particles located at different positions. Okay, I represent the Cartesian coordinate x1 y1 z1 to represent the position of the first particle, and x2 y2 z2 represents the position of the second particle. In such case, the wave function of the system containing these two particles can be written as psi of x1 y1 z1 comma x2 y2 z2. Okay, and comma t if it is a time dependent system. Otherwise psi of x1 y1 z1 comma x2 y2 z2, that is the position of both the particles. Suppose there are n number of particles, then this wave function becomes complicated. It contains n into 3, that is total 3n parameters, okay, 3n coordinates, because each particle has 3 coordinates x1 y1 z1. Suppose there are n particles, okay, each particle having 3 coordinates, there are totally 3 into n parameters present in the wave function. So the wave function becomes more and more complicated as you have more number of particles present in the system. However, okay, whatever is the complexity of the wave function, you can simplify this wave function and write it as a product of two wave function, okay, as psi of x1 y1 z1 into psi of x2 y2 z2, where this represents the wave function exclusively representing the state of the first particle, that is, it depends only on the position of the first particle, into the second wave function which exclusively depends on the second particle, that is the position of the second particle. So whatever is the complexity, okay, whatever complex is this wave function, it can be simplified and written as product of wave function associated with each particle, provided if the particles do not interact with each other, okay, if they do not interact with each other, okay. If there is n number of particles, then the overall wave function can be written as product of n number of wave function, where each wave function deals with one particle. And again, this assumption is valid that all those n particles are not interacting with each other. So you can simplify a wave function like this if the particles do not interact with each other, and this condition that I have written here is nothing but the method of separation of variable, okay. So what does postulate 1 tells us is how to describe the state of a system. In order to describe the state of a system, we require what is called as the wave function, okay. This is only what the first postulate has to say. Now the question arises, okay, the state of a microscopic system is defined or described in terms of the system psi of x comma y comma z comma t. But the question is how this wave function describes the state of the system. Okay, if I have solved the Schrodinger wave equation and obtained a wave function, using this wave function, how can I describe the state of a system? For example, how can I calculate the position of the particle in the system, or how can I calculate the total energy of the particle, or how can I calculate the probability of finding the particle at a particular point, or how can I calculate the momentum of the particle? That answer is not given by the first postulate. What first postulate has to say? The first postulate just says that in order to describe the state of a system, the first thing you should know is the wave function that is obtained by solving the Schrodinger wave equation. So once I have this wave function obtained by solving the Schrodinger wave equation, what should I do with the wave function so that I can describe the state of the system? That is given by the second postulate of quantum mechanics. So let us now state the second postulate of quantum mechanics. And remember, whatever postulates I am stating here now, we already know these points, but we have not, okay, methodologically discussed this, okay. While we applied Schrodinger wave equation to particle in a one-dimensional box or three-dimensional box, we have already discussed all these points, but now we are systematically placing them in the rule of in the form of set of rules, okay. The second postulate of quantum mechanics states, for every measurable physical quantity or observable, okay, so for every observable or measurable physical quantity such as position of the particle or the energy or the kinetic energy, for every measurable quantity such as total energy E, or it may be kinetic energy, or it may be position, or it may be momentum, whatever it is, okay, there is a corresponding operator in quantum mechanics. Okay, so this is the statement of the second postulate. What does it state? For every physical quantity that can be measured or every observable, okay, such as energy, kinetic energy, position, momentum, angular momentum, whatever it is, you have a corresponding operator in quantum mechanics to calculate it. This is also already known to you, because when we discussed the concept of operators, we came across a very important operator called Hamiltonian operator. And also when we solved the Schrodinger wave equation, we discussed about this Hamiltonian operator. There I already told you that Hamiltonian operator is an operator corresponding to the total energy. So if I want to calculate the total energy, I need to use the Hamiltonian operator. So that is summed up as the second postulate of quantum mechanics. So for every measurable physical quantity, you have an operator in quantum mechanics. So I will list out some of the operators, okay, and these operators that I am listing out can be derived in a mathematical way, but we need not to derive all those things here. So I will list some of the operators that we use in quantum mechanics. Okay, so name of the observable, okay, the operator, and the symbol for the operator. Okay, the first observable, okay, for example, momentum. Okay, if the system is a one-dimensional system, the momentum is given by I into h divided by 2 pi into d by dx. So this is the expression for the momentum operator of the particle traveling along x-axis, where I is the imaginary number, and this is the symbol for this momentum operator px cap, where x signifies the direction, that is, it is x-axis. Suppose if the particle is in three-dimensional system, if the particle is moving in three dimension, the corresponding expression for operator will be I h by 2 pi, okay, into I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z, which is nothing but, this is nothing but the del operator. So we can write it as minus I h by 2 pi into the del operator. Okay, and the symbol for this operator is p. So this is the expression, these are the expressions for the momentum operator along x-axis, and this is the overall three-dimensional form. Okay, similarly you can write the expression for the kinetic energy operator. Okay, the kinetic energy operator is minus h square divided by 8 pi square m into d square by dx square if the particle is moving only along x-axis, and the corresponding symbol for this operator is E kinetic with a cap. Okay, and you can write it as x because it only is in the x-axis. The overall three-dimensional operator, okay, is minus h square by 8 pi square m into d square by dx square now becomes dou square by dou x square plus dou square by dou y square plus dou square by dou z square, which is nothing but the Laplacian operator del square. Okay, the symbol is E bar kinetic. Okay, so these are the expression for the corresponding kinetic energy operators. Okay, similarly I can give some more example. Observable operator, the symbol. Okay, if position operator, okay, so the position of the particle. Okay, so position of the particle, if it is only along x-axis, the operator is x, which is a multiplication operator. Okay, and the symbol is x cap. If it is in three dimension, if the particle is moving in three dimension, the corresponding operator will be I into x plus j into y plus k into z. Okay, a vector operator representing the position operator, where I, j, k are the unit vectors along x-axis, y-axis and z-axis, and this is represented by the symbol r cap. It is represented by the symbol r cap. So this is a three-dimensional position operator, whether this is a one-dimensional position operator, and they are multiplication operators. And I hope you remember what do you mean by multiplication operator. The fourth observable is potential energy. Okay, again potential energy is a multiplication operator. We simply multiply the expression for formula for potential energy. It is represented, the operator is v of x. It is a multiplication operator and it is represented by the symbol v. Okay, if it is three dimension, then the potential energy is v of x comma y comma z. It is also a multiplication operator. It is also represented by the symbol v cap. Okay, so here the potential energy depends only on the x position of the particle. So the only depends on the x position of the particle, whereas here the potential energy depends on x, y and z, that is the position of the particle in three dimensions. So similarly you can write the expression for total energy. Okay, again if the particle is traveling only along x-axis, then the total energy is sum of kinetic energy and potential energy. So the total energy operator should also be the sum of kinetic energy operator and potential energy operator. So it is minus h square by 8 pi square m into d square by dx square plus v of x. If it is in three dimension, the operator is minus h square by 8 pi square m into del square plus v of x comma y comma z is the three-dimensional total energy operator, and you know that they are represented by the symbol h, capital H. This is nothing but the Hamiltonian operator, a very important operator in quantum mechanics, because they represent the total energy operator. One more operator, okay, which is not familiar to you now. We will discuss about this later in detail. One of the important operators and one of the important physical quantity called as angular momentum. Okay, angular momentum. Okay, so this angular momentum in one dimension, okay, in only consider three dimension, because since it is a rotational system, either we have two-dimensional or three-dimensional components only. So the angular momentum has three components: the component of the angular momentum along x-axis, y-axis and z-axis. So they are represented by the symbol Lx cap, Ly cap and Lz cap. So these are the representation for the angular momentum operators of x-axis, y-axis and z-axis. Okay, the expression is minus IH by 2 pi into y into dou by dou z minus z into dou by dou y. So this is the x component of the angular momentum operator. Okay, so what are these operators, why these operators have this type of expression, we will discuss it later. We will just write down some of the important operators. The y component of the angular momentum operator is minus h by 2 pi into z into dou by dou x minus x into dou by dou y. This is the y component. Finally, the z component is minus h by 2 pi into x into dou by dou y minus y into dou by dou x. This is the z component. I have made a mistake here. The y component is y into dou by dou, sorry, z into dou by dou x minus x into dou by dou z. Okay, finally this is the z component of the angular momentum operator. Okay, so we will discuss about the angular momentum operator again. So what does the second postulate tell us? The second postulate tells us that for every measurable physical quantity, okay, we have a corresponding operator in quantum mechanics. So by using these operators, it is possible to find out the values of the corresponding physical quantity. Okay, this is just what the second postulate has to say. Now immediately it raises a question. Okay, we have an operator to calculate the value of a corresponding physical quantity. For example, I have Hamiltonian operator or a total energy operator to calculate energy. But how to calculate using this operator? This gives rise to the third postulate of quantum mechanics. The third postulate of quantum mechanics tells us how to apply this quantum mechanical operator, okay, and calculate the value of the physical quantity. This is nothing but the third postulate of quantum mechanics.